We always hear about machines learning, right? It feels like this magical black box. We feed it tons of data, and somehow it just spits out these incredible predictions. But what's actually going on under the hood? Well, today we're going to pull back the curtain on the statistical engine that makes it all possible. Let's get right into it. So, when we say a machine learns, what do we actually mean by that? Is it thinking like a person? Is it understanding concepts? Not exactly. In the world of machine learning, the answer is actually a lot simpler and way more concrete. It's estimating. Yep, that's the big secret right there. This whole complex, incredible process of machine learning, it really just boils down to one thing: making a really, really good guess. An educated guess about the world based purely on the data it's seen.
And believe it or not, there's a whole science dedicated to this. It's called estimation theory. You can think of it as the official rulebook for making smart guesses. It's the mathematical framework that gives us all the tools we need to find the best possible values for a model's parameters.
Okay, before we go any further, we need to get two key terms straight because they are absolutely crucial. First, you have the estimator. That's the method or the formula you're using to make the guess. It's the tool. Then you have the estimate. That's the specific value or the answer that your tool spits out. Simple, right? The tool and the answer it gives. I know, this can all sound a bit abstract. Estimator, estimate. So let's make this super concrete with an analogy that everyone can understand. We're going to talk about a simple thermometer.
Okay, so check this out. The real temperature of the room, that's the thing we want to know but don't. That's our unknown parameter. Now, the thermometer you're holding, the actual physical tool you use to measure it, that's your estimator. And that number it shows you, say 20 degrees, that specific reading, that is your estimate. See how it all fits together?
And here's the key takeaway, the most important thing to get from this analogy. Your estimate is only ever as good as your estimator. I mean, if you're using a cheap, broken thermometer, you're going to get a lousy guess of the temperature, right? It's the exact same principle for a machine learning model. So that leads to the obvious next question, right? How can we tell if we have a good estimator? Whether it's a thermometer or a complex AI, how do we grade it? Well, statisticians actually have something like a report card for this, and there are three main things they look for.
Yep, these are the big three: unbiasedness, minimum variance, and consistency. Let's quickly break down what each one actually means.
First up, unbiasedness. All this means is that, on average, your estimator hits the bullseye. It doesn't have a built-in error. Think about our thermometer again. An unbiased one might read a little high one minute, a little low the next. But if you took a ton of readings, the average would be the true temperature. It's not systematically off, like always being 2 degrees too hot.
Okay, second, minimum variance. This is all about stability. Imagine you have two unbiased thermometers. Thermometer A gives you readings like 20, 20.1, 19.9, super tight cluster. Thermometer B gives you readings like 15, then 25, then 20. I mean, they both average out to 20, so they're both unbiased, but which one would you actually trust? The first one, of course. You want an estimator that gives you consistent, stable answers, not one that's all over the map. And number three is consistency. Now, this one is huge, especially for machine learning. A consistent estimator is simply one that gets more accurate the more data you feed it. The more information it has, the closer its guesses get to the real answer. It's the entire premise of training a model, right? More data should lead to a better model. That's consistency in action.
All right, so we've got the theory down. We know what a good guess should look like. But how do machines actually find these good parameter values in practice? How does it go from theory to a working model? Let's take a look.
Well, one of the most popular and powerful methods out there is called maximum likelihood estimation, or MLE for short. The core idea behind it is actually pretty intuitive. It kind of works backwards from the data you already have, and it asks one very clever question. It asks, hey, looking at all this data I've collected, what set of parameters would make this data the most likely to have happened? It's like being a detective. You have the evidence, the data, and you're trying to find the story, or the parameters, that best explains that evidence. It's searching for the parameters that maximize the likelihood of the data you've observed. And here's a really cool connection. If you've ever done any basic stats, you've probably heard of the least squares method, right? The one used to draw that perfect line of best fit through a scatter plot. Well, guess what?
that's just a special case of maximum likelihood estimation. It's MLE in disguise, working under the assumption that the errors are normally distributed. Now, it's worth mentioning that MLE is a cornerstone of one of the two major schools of thought in statistics, the frequentist approach. Frequentists believe that the true parameter out there in the world is some fixed, unknown constant. Then there's the other team, the Bayesians. They see things a bit differently. They think of parameters as things we can have beliefs about, and that we can update those beliefs as we get more data. Two different philosophies for tackling the same problem.
This quote really nails the difference. For a frequentist, parameters are fixed and data is random. For a Bayesian, the data you've seen is fixed, and it's your belief about the parameters that is uncertain and can change. It's a really fundamental difference in how you view the world.
Okay, so why does all this matter? Why dive so deep into estimation theory? Because it is, without a doubt, the foundation of trustworthy AI. The entire performance and reliability of a model, any model, hinges on how good it is at this one fundamental task, making good guesses. So let's just quickly recap the big points. First, machine learning is really just a fancy term for parameter estimation. Second, a good estimator has that trifecta of qualities. It's unbiased, has minimum variance, and it's consistent. Third, methods like MLE are the engines that actually find these parameters. And finally, and this is the big one, the quality of an AI model is directly determined by the quality of its statistical estimator. It's that simple.
And that really leaves us with a final, massive question to chew on. If all of this incredible AI is fundamentally built on making sophisticated guesses, what does that mean for us? When we're talking about self-driving cars, or medical diagnoses, or systems that control our financial markets, how do we decide when a good guess is actually good enough?